Okay, thank you for deciding to watch my video, and thank you to the organizers for giving me an opportunity to talk a bit about my research in this new format. So I'll be talking about norm form equations and linear divisibility sequences. So let me start with a definition. So let's take K to be a number field, and we'll let W be any Q-linearly independent subset of K. We'll define the norm form associated to the set W to be the rational form, defined by taking the norm of linear combinations of elements in the set W. You can show that this is, in fact, a rational form, and so you can pose this Diophantine problem of finding all integer solutions to equations of this type. So let me give you two examples to show you that this is likely familiar and also an interesting problem. So first of all, let's consider the Pell equation x squared minus dy squared is equal to c. Observe that you can factor on the left-hand side of this equation to write this as the norm of elements x plus y square root of d. So this is the norm over the number field q join the square root of d. And so this is a norm form with defining set 1 square root of d in this number field k. So all of the Pell equations are norm form equations. Second example, if you take any number field k and let w be an integral basis for k, then these two norm forms are solutions to these two norm forms give you all of the elements in the ring of integers of norm plus or minus 1, which gives you all of the units in k. All right, so I want to tell you about how one typically characterizes these solutions. So to start, let's make this observation that if you have some norm form with defining set W, you can define this module, this Z module M, generated by the set W. And what I'd like to do is I'd like to work over here sort of in the land of modules instead of with these Diophantine equations. But if I want to do that, I don't want to have to keep my basis fixed. So what happens if I change to another basis, let's call it T, then I may get some different norm form, but it's a short exercise to show that these two forms are integrally equivalent. And so up to integral equivalency, which is really what you want for Diophantine problems, every norm form is associated to a unique module in K. That is, if we want to find solutions to a norm form equation, this is the same thing as finding elements in the associated module of fixed norm C. So oftentimes we'll just instead look at elements in some module. Okay, so here's how this characterization typically works. I'll talk about the characterization in the full case. So in the case when your module is not full, the situation is a bit more tricky, but this has been studied quite a bit by Schmidt, for example. So for us, let's assume our module is full. And let's let O sub m denote the coefficient ring of our module. So by that, I mean the elements in the number field so that when I multiply by elements in my module, I stay in my module. Let's let um plus denote the positive unit group of my module. So these are the elements in the coefficient ring of norm 1. And it's a very classic fact to show that all of the elements in such a module of fixed norm C lie in finitely many disjoint families of this form. So you can show that the coefficient ring of a full module is an order in a number field. And so Dirichlet's unit theorem applies here and tells us that the positive unit group is a finitely generated abelian group. And moreover, it has positive rank as long as your number field is not the field of rational numbers or imaginary quadratic. So sort of the trouble with this characterization is that it's generally quite challenging to find these elements, alpha I, and generators for the free part of the positive unit group explicitly. So if you want explicit information about these solutions, this doesn't quite get you there. But what I would like to use about this characterization is that as long as we're not in one of these two cases for our number field K, then I can take elements in the free part of my positive unit group and generate infinite sequences of solutions to my norm form equations. So this is what I want to focus on. So let me be a little bit more precise. So say that you found some element in your module with the norm that you want. Then for an element in the free part of your positive unit group, I'll let alpha k denote this sequence where I'm taking the element beta, leaving it fixed, and multiplying that by positive integer powers of my unit epsilon. Observe that this is actually an infinite sequence because I chose a unit of infinite order. I chose this in the free part. For every power k, this stays in my module because I chose my unit to be an element in the coefficient ring. And also all of these elements are of fixed norm C because I chose a unit in the positive unit group, so it has norm 1. So I found this infinite sequence of elements in my module of fixed norm C. How do I translate this back to my Diophantine problem? Well, recall if I write this in terms of some basis for my module, then I get these tuples of solutions to either my original norm form equation or a norm form equation where I've replaced this by some integrally equivalent form. So it's these sequences here, this x1 of k to xn of k, that I would like to focus on in this talk. So let's give them a name. Let's call these integer sequences xi of k the coordinate sequences of alpha k with respect to our choice of basis w. Okay, so these sequences turn out to be quite nice, so I want to write this fact down and call it a key lemma. So the coordinate sequences of my solution sequence, alpha k, turn out to always be linear recurrent sequences. And moreover, I can read off their recurrence if I know information about the minimal polynomial of my unit. Okay, so let me just give a very quick sketch of this fact, just so you can sort of see the main part of where it's coming from. So if you choose some basis for your module and write your solution sequence with respect to this basis, you can show that there exists this dual basis, so that if I plug a dual basis element into like the left-hand slot of my trace pairing and my solution sequence into the right-hand slot, then I exactly pick out the ith coordinate. And then this sort of gives you a way to show that the sequences that you want satisfy the correct recursion. Okay, so this lemma, this key lemma, first of all, is going to give me a very nice observation. So let's go back to the case where I have a real quadratic number field and some full module in this number field k. Recall that this corresponds to the Pell equation case. So if I find an element in this module and I take a unit in the free part of the positive unit group, I can construct these solution sequences in the same way as before. The proposition is that I can always find a choice of basis for my module so that for whatever coefficient sequence I want, these coefficient sequences can be seen to be linear divisibility sequences. And by that I mean, whenever the indices of the sequence divide each other, so do the terms of the sequence. So just a quick sketch of this fact as well. So this follows pretty quickly from our key lemma. This follows because our key lemma says that these sequences are order 2 linear recurrent sequences. And so I can show that there exists some basis for my module so that whichever coordinate sequence I want has 0 value equal to 0. And you can show that all order 2 linear recurrent sequences with this initial value are just constant multiples of a Lucas sequence. And Lucas sequences are well known to be divisibility sequences. So this divisibility follows. Okay, so this leads me to a question. So my question is, does this happen in other cases? Or is this really special about the fact that I just happen to end up with an order 2 recurrence and those all happen to be Lucas sequences? So more precisely, if I have a number field k and a full module in that number field, suppose that we have the usual players. So suppose I have some element in my module with the norm that I want, a unit in the free part of the positive unit group, and I create these solution sequences in the same way as before. My question is, are there other examples so that under some choice of basis for my module, the coefficient sequences of alpha k are linear divisibility sequences. So let me give you a couple pieces of motivation for why one might ask this question. So first of all, we mentioned before that finding explicit information about solutions to norm form equations is generally quite hard. But divisibility sequences have particularly nice factorization properties. And so if we could find other examples of norm form equations with this extra structure, perhaps that could be helpful in learning explicit information. I'll say the trouble with this question is that as soon as the degree of your unit is bigger than 2, you're looking for higher order linear divisibility sequences, which tends to be quite challenging as well. So it's difficult to say things very broadly and generally, but what we can show is that this does happen in at least one other type of case. So here's my theorem. So let's let M be a full module now in a quartic number field K with the following setting. So my quartic number field should have a real quadratic subfield containing a unit of positive norm, so that when you take the square root of that unit, you stay in your quartic number field. Then what I can show is that there always exists a basis for either your module or perhaps a finite index submodule, which I'll tell you about in a moment, so that if you write your solution sequence in terms of this basis, whichever coordinate sequence you want, it is a linear divisibility sequence. Okay, so let me give you some ideas for what's involved in this theorem. So let's take alpha k as before. So now my unit is the square root of epsilon. We can use our key lemma from earlier to show that the coordinate sequences of alpha k satisfy this order 4 linear recurrence sequence. Okay, and then you can prove this sort of elementary lemma that says that if you have an order 4 linear recurrence sequence satisfying the recurrence we found above, that has these initial conditions, then you get that the sequence is a linear divisibility sequence. Very quickly, I'll just say the sort of idea for this lemma is after some amount of work, you can show that the terms of this sequence x of k are in the even terms Lucas sequences, and in the odd terms are a sum of 2 consecutive terms in the Lucas sequence. You can then use this observation with various Lucas sequence identities to get the divisibility property that you want. Okay, so this lemma is saying that our coordinate sequences satisfy the correct recursion that we want. So what else do we need to do? Well, we need to show that they also satisfy the correct initial conditions. So we need to find a basis so that my coefficient sequence, my coordinate sequence, sorry, has these initial conditions. So I've scaled my initial conditions from my previous lemma just by some constant multiple, so I won't lose anything about divisibility. So the question is, when can I do this? When can I find these initial conditions? Well, I can show that I can always do this for this module I'll call M prime, which is beta times z adjoined the square root of epsilon. Even if this isn't the module we started with, it does turn out to always be a finite index submodule if the square root of epsilon is degree 4. And in the case where I don't know what the module is, if I at least know how this finite index submodule is sitting inside of my module with respect to these invariant factors, then I can find these correct initial conditions as well. So I want to talk about part 1 of this sort of generally, and I'll give you sort of a longer example to explain or to show you when you can apply part 2. Okay, so let's remind ourselves what we have. We have this solution sequence and this module beta times z adjoined the square root of epsilon. I want to note a couple of things. So first of all of the terms of this solution sequence are contained in this module. So this is a good submodule to be looking at. And also this submodule has this basis. So recall what we need to do is find a basis for this module M prime, so that if I write my solution sequence in terms of this basis, then the following takes place. So over here on the left-hand side, I'm saying I want these initial conditions. And on the right-hand side, I'm reminding you where these initial conditions come up. They come up as the first coordinate when I take various powers of square root of epsilon and multiply that by beta. So I'm going to put this whole picture into a matrix and say that what I really want is I want this equality to hold. But the nice thing is that this vector on the right-hand side of the equality is a basis for M prime. So all I really need to do is figure out how to fill in this matrix A to make it a GL4Z matrix. And you can do it in this way for all the time. So you can always let A be 1, and then you can fill in the rest of your entries in this way, and you get some GL4Z matrix, which means that if you solve for W1 to W4, you get a basis for this module M prime. And lemma 1 says that means if we write our solution sequence in terms of this basis, the first coordinate sequence should be in LDS. Okay, so this is sort of part 1 of my theorem. For part 2, it's a little bit more like more linear algebra than you probably want to have to see, so I'm just going to give you an example. So here's an example where this part 2 applies. So let's let K be this, this biquadratic extension, Q adjoins square root of 2, square root of 3, and let's let M be this full module in K. Let's let epsilon be this unit of positive norm contained in one of the real quadratic subfields. And then when you take the square root, you can observe that this is contained in the positive unit group of your module. And so I'll let alpha k be just take positive integer powers of square root of epsilon. This gives you a sequence of elements in this module of fixed norm 1, just like before. And recall what we need to do is we need to find a basis for this module so that I have the correct initial conditions, which are here in the first column of my matrix. So the trouble now is that this vector over here is no longer a basis, but it does form a basis for a finite index submodule. So if I write this in terms of some basis for my entire module, then this matrix B should be in GL4Q. And so really all you need to do is just multiply on the left-hand side by B inverse, and then show that you can fill in A so that B inverse times A is GL4Z, and that will give you a basis for M. The other sort of thing you want to observe is that you can choose whatever basis you want for the bigger module in this setup. So you want to sort of mess with it so that the matrix B is nice, so that it's not so hard to invert. Okay, so I'll spare you all of those details and just say with some linear algebra, you need a bit of geometry of numbers. You can find this basis for your module that makes the matrix be nice so that you can fill in your matrix over here to get your basis for your module, which I've computed for you on this line. Okay, so, and then this lemma says that if we write our solution sequence in terms of this basis, we should get that the first coordinate sequence is a linear divisibility sequence. So I figured I would end in my last minute by just showing you some tables. So just to remind you where we are, we have this unit 5 plus 2 square root of 6, and I'm looking at powers of the square root of that unit in this module. And we have sort of 3 different choices for our basis. So here's the basis one would usually choose for z adjoins square root of 2 square root of 3. I'll call that basis 1. We also just constructed a basis for our module using a bunch of linear algebra and geometry of numbers. And then I want to recall our basis from earlier for this finite index submodule computed in this way. So here's what the tables look like, just very quickly. Using the original basis, here are all of your coordinate sequences. And you can stare at this for a while if you want, but there aren't very many patterns appearing. If you change to the basis that we just found, you can check, at least for these first 10 terms, that you're getting the divisibility property we wanted. But you still don't, it's still difficult to say what's happening with the rest of these coordinate sequences. Sort of the nicest situation is if you take this basis for the finite index submodule, your tables look something like this. So you get a linear divisibility sequence in the first, for the first coordinate sequence. And I've sort of highlighted in red here to show you what's happening. The rest of the coordinate sequences are sort of following along with the first one. And actually, we can show in general, the table always looks like this. So you get this first sequence I've highlighted here in blue, which we can show as a linear divisibility sequence. And all of the other coordinate sequences alternate between 0 and a term in a Lucas sequence. And so this is particularly nice if you're interested in studying things like prime divisors of solutions to some norm form equation or something like that. So, okay, I'll stop there. Thank you so much for listening.